So in this video, we're going to take a look at ionic equations. Now, ionic equations, when we think about an ionic substance, let's say we have sodium chloride. Right? Sodium chloride, when we're looking at that solid, exists as little sodium ions and chloride ions, all nicely organized in that crystal salt in a beautiful crystal lattice structure. And those ions are all locked in place. But when we go and put it in water, right, when we take that NaCl and we drop it into a container of water, we're going to see those ions separate, right? The substance dissolves. And when it dissolves, it breaks into its ions. It dissociates. And when it dissociates, we end up with sodium ions, right? So just think about those ions. But now they're separated from their chloride ions. So if our chloride ions are over here in the solution, or maybe our chloride ion is over here, every single ion is now separated from one another, and they can move around. That's the idea of dissociation. And that is how an ionic substance, when it dissolves, what actually happens. Now, sugars, things that are molecular, don't do that. The molecule, one molecule just separates from another molecule when it dissolves. The molecule doesn't break apart, not like an ionic substance. Ionic substances, when they go into water, will break apart into the different ions, and we call that dissociation. So it's important when we're looking at a reaction, if we're dealing with sodium chloride in a chemical reaction and it's aqueous, right? You see the AQ beside it. That means it's in solution, it's in water. So we need to recognize that really what that means is it's actually existing as Na plus ions and chloride ions. That's really what you have in your solution, right? That's what we're actually seeing. It's no longer Na and Cl stuck together. It's actually existing like this. But to make our lives easier in a chemical reaction, sometimes we just write it as NaClAQ. But there are certain types of equations where we might want to separate them out. Okay? The first type is the one that I just drew for sodium chloride. This is an ionic equation. All right, so an ionic equation looks like this, right? Where our sodium chloride is going to split into sodium ions and chloride ions. It dissociates into those ions. And we can do this with any substance, any ionic substance that dissociates, we can split it into its ions. And to help us remember that, all we need to do is take a look at our solubility rules, and I have those down here, right? So for any of those substances that are soluble, we can write a dissociation equation. So something like, if I look at something that's really soluble, let's say ammonium with hydroxide, right? It's highly soluble. So if I have ammonium hydroxide, and I have that solid and I put it in water, I can write a dissociation equation of NH4 plus and OH minus. So the ammonium hydroxide, when I put it in water, I get dissociated ions of NH4 plus and OH minus. So this is how we can use our solubility rules to help us identify what we can write as ionic equations and what we can't. Something like lead 2 down here, so my lead 2 right here with a chloride is low solubility. So if I have PbCl2 as a solid and I put that in water, it does not dissociate, right? So I can't have an ionic equation for PbCl2 in that form. I can't have the solid breaking into the ions if that dissolves. So let's take a look at another example here of what potentially we might do with dissociation equations or ionic equations. And we'll introduce a few little key pieces for you. So these things that we're going to look at, we're going to talk about a total ionic equation and a net ionic equation. What it essentially means is that any chemical reaction that we can write down, anything that's aqueous, we're going to split it into its ions, like because they're going to be dissociated. and anything that's not just stays whatever state it is. So if I look at this particular question, I've got silver nitrate and sodium sulfate. This looks like it could be a double displacement. So if it's going to be a double displacement, I'm going to end up with Ag2SO4 and NaNO3. Now, if I go back up to my substances in my solubility rules table, and I look at sodium nitrate and silver sulfate, so all nitrates are soluble, so the sodium nitrate is going to be soluble. But if I look at silver and sulfate, that's a low solubility. So that substance is going to precipitate. So when I am looking at what state I have for this double displacement reaction to take place, we know that one substance has to be a solid, the other substance should stay in solution. So there's my double displacement. Now, we want it balanced, so I'll put our 2 in there to balance the silvers, and a 2 in front of NaNO3, that'll balance the sodiums and nitrates. So now there's my balanced double displacement reaction. To put it into a total ionic equation, so sometimes we call this a TIE for short. Okay, so I'll just write that up there so that you know. Okay, so that's our TIE. We take anything that's aqueous and we dissociate it. So if I have silver nitrate, that really means I have silver ions, so I have Ag+, and I have nitrate ions, NO3-. And because there's 2 of them, I should have a coefficient 2 for my silver and a coefficient 2 for my nitrate ions. So anything that's aqueous, we're going to do that same thing. So I'm going to do that with I'm going to have 2 sodiums from the sodium sulfate. I'm going to have 1 sulfate ion. And then that's going to produce silver sulfate. You'll notice this is not an aqueous, so I don't split it apart. It stays as the solid. And then I'm going to split up my sodium nitrate because sodium nitrate is aqueous. Right? So it's actually dissociated, so writing it as 2 separate ions really makes more sense as to what's happening. And that should be a negative sign right there. So there's my total ionic equation. Everything that could be broken into the different ions, dissociated into the different ions is shown. Anything that can't stays in the form that it is. Now, that's all fine and dandy. There's a lot going on there, but the other piece that sometimes we like to include is the net ionic equation. So we shorten that, we call it NIE. Okay, so that net ionic equation, NIE. And what the net ionic equation does is it takes out any spectators. Now, think about a sporting event. I know we can't be doing sports right now, but if you think about a sporting event, there are people that sit there and they watch the game take place. They're not involved in the game. They're just watching. It's the same when we talk about spectator ions. They're not actually involved in the reaction. They just are in the container watching it happen beside them. So those would be substances that occur on both sides of the arrow. So if I look here, I've got 2 sodiums on my reactant side, and I have 2 sodium ions on my product side. Nothing happened to them. They started as sodium ions, they finished as sodium ions. They are spectators, okay? So sodium is a spectator. Nitrate's a spectator, right? Both of these are spectator ions. So they don't do anything. So in essence, they're not really part of the actual reaction that's taking place. The only thing that's reacting is what we have left over, and that's what we call our net ionic equation. So in this case, the only thing that actually reacts is the silver ions and the sulfate ions. That's it. The sodium and the nitrate, they did not react. The only reason they were there is to get those other ions into solution so that we could have 2 solutions that we would mix together that would actually make a precipitate. So this is our net ionic equation. We got rid of all the spectators. right? All the spectator ions are gone. This is what is actually reacting. So this is what we do with our dissociation equations and ionic equations. If you hear those things, this is what we're talking about, right? Dissociation, split them into ions. So our AgNO3 becomes Ag plus and NO3 minus. If you talk about total ionic equation, then we're looking at a reaction as a whole and dissociating anything that's aqueous. And our net ionic equation takes out those spectators so that all we're left with is the substances that actually reacted.